vai dar um tempinho? Vamos começar?
Ainda acho que tem dois minutos. Um minuto. 2 minutos.
Está transmitindo para o YouTube?
Gravar, depois vai subir para o YouTube.
Hello. Good morning, everyone. So we're gonna get started with this seminar. So as you know, so every Wednesday at 11 a.m. now we're gonna host the seminars of IIP. So it's a pleasure to be the host of Dmitry. I would say from his CV, everything you can see from his CV, that he graduated from New Jersey University, and after that he followed a postdoc at Tel Aviv University, and joined IIP in 2011. So everything I'm saying you can read from his CV. But there I would say that's my saying now that he has been a key researcher of IIP since he joined us. So thank you so much for giving this talk. So he's going to talk about quantum entanglement and topology. Take your time.
Thank you very much, Fernaldo, for a very nice introduction. And I thank everybody for coming today. So I'll be talking about connection between well, the phenomenon known as quantum entanglement, which is very much studied recently, and topology. So here's the plan of my talk. I would like first I will introduce what is called topological quantum field theories, but I will introduce it on quite pedestrian level. In fact, my talk is planned to be quite introductory, so I apologize for those people who know this already. And well, this construction in some way is quite known and under the name of topological quantum computation, but instead of rushing to introduce quantum gates and quantum computation, I'll make a step back and I will discuss general properties of this construction. And the question that I will be asking is what can we learn from this kind of presentation, a different way of presentation of quantum mechanics. So in particular, I will use this construction of topological quantum field theories to discuss quantum entanglement, properties of quantum entanglement, and classification of quantum entanglement. And I very much hope to come to this last part, which is a few examples of quantum algorithms built using this approach, this technology. So here, this is a picture of Kipo. This is a communication tool known to people who lived in South America some years ago. So what my plan in the end is some kind of take over and introduce a quantum version of Kipo. So that's my final plan in this talk. Okay, let me start. So as I said, I will introduce some notion of quantum mechanics, and it will be somewhat standard notion of quantum mechanics. So what do we need for quantum mechanics? What quantum mechanics is? So I'll need Hilbert spaces. They can be simple Hilbert spaces, like a simple two-dimensional Hilbert space of a single qubit, which means it's a dimension two linear space, spin up and spin down. I can have a tensor product, a more complex Hilbert spaces. They can be defined on their own, or they can be understood as tensor products of basic Hilbert spaces. Clearly, I need states, and I need all kind of linear algebra operations on states. So I need, for example, I need to know how to compute scalar products. I want to build tensor direct products of states, which are states in larger Hilbert spaces and so on. And I will need operators. So operators, for operators, I also need some standard operations like computing traces, matrix elements, and so on. There will be no Hamiltonian in the sense that we learn in the standard course of quantum mechanics. And the reason for that is topological theories are special. There is no local Hamiltonian. So what there is actually a number of discrete operations, and the evolution is built from these discrete operations, and you can think of them as, pieces of some discrete Hamiltonian. Okay, so let me start building this quantum mechanics. So this is a definition due to probably Michael Atiyah in the late 80s, and, with the contribution of Edward Witten and other mathematicians. And well, this is known under the name of category theory of definition of topological quantum field theories, but well, there's not much of category theory that will appear here. So what I will just say that I want to define a map between two sets of objects. So one will be topological spaces like spheres, tori, and so on, and linear spaces like Hilbert spaces. So here, for example, I have a topological space. Here is just a disk, but this disk can be a sphere, can be any other space. And my map that I will define will put some linear space into correspondence with this surface. Well, let's think that this surface has dimension d, so this surface sigma is mapped to some linear space, which we call H. It will be a Hilbert space. So what will be states in this Hilbert space? So what I will do, I'll take this sigma and I'll start gluing high dimensional spaces, so dimension d+1 spaces, to this boundary sigma. So I will say that states are all manifolds of dimension d+1 whose boundary is the surface sigma. Well, I will also need operators. So operators apparently will be these d+1 dimensional spaces, but that have two boundaries. So they will be space whose boundaries is a union of two surfaces sigma. Well, is that unique? No, I mean, any functor with these properties, which I will explain now, I will call a topological quantum field theory. So, well, in the end, I'm constructing this map to linear spaces. In linear spaces, I have operators. Operators, I know how to multiply. So I want to have something similar in the case of topological spaces. So what is multiplication in terms of topological spaces? Let's say I have two manifolds, M1 and M2. They both have two boundaries. So what is multiplication? I can glue them. If they have a same kind of boundary, I can glue them along this boundary and produce, this new cylinder is a new space, which I will call a composition of the two spaces here. So this is kind of a picture of a product in my linear space, right? So this is how I somewhat image the multiplication of the operators using my topological spaces. Well, I can use also the connection between states and operators. Well, in fact, we like to think of states and operators as matrices, right? So state usually a vector, right? But vector is also a matrix. So whatever I have, a state or operator, is some kind of matrix. So I can also understand state as a kind of evolution, but in this case of something with empty boundary, so no boundary at all, to some normal boundary. So state is kind of operator, so this naturally defines me action of operators on state, so I can glue an operator to a state and get a new state. Okay, so that's more or less the general picture. I can specify some additional axioms here. Well, you can already guess what the scalar product in this case is. So let's say I have two vectors and they have the same boundary. So I can glue them together and I can get something which has no boundary. So we call it a closed space. So closed space denotes a scalar product. And well, there's an axiom which says that if we have a manifold M which has no boundary, then my map should put into correspondence to this M some zero-dimensional linear space, which is just a complex number. So this is an example of such a complex number. Any closed manifold, it can vary depending on internal structure. There can be some non-trivial topology, but this is mapped into a number. I should have an identity operator. So identity operator is this kind of featureless cylinder. It doesn't have any internal structure. If I glue it to any state, it will not change the topology of the state. So this is an example of identity operator. So the final important property is if I have two sigmas and they are disconnected, then this will be mapped to a linear tensor product, direct product of two Hilbert spaces. So that will be important in the discussion of entanglement. Well, this seems a bit like ad hoc construction, but in fact, it is motivated and can be realized by certain quantum field theories. In particular, if you have a quantum field theory with an action which doesn't depend on a metric, we also call it a topological theory. So we can compute what is called functional integral, and functional integral will be a realization of this map F, which appeared on the previous slides. So in particular, let's consider a functional integral of the action of this theory. So this is the action of a theory which is called Chern-Simons. And you see in the definition, you have an integral over space M. So in my functional integral, I'll integrate this exponential factor, and the integral, the exponent will depend on this space M, and this M can have boundary or may not have boundary. And if it doesn't have boundary, then the functional integral is just a number. This is what we wanted. Or if it has a boundary, we have to specify boundary conditions for fields on this boundary. So in this way, as you know, well, if you studied functional integral, you must know that this defines your state in the Hilbert space in quantum theory. And then what is scalar product? Well, you can take a product of two integrals, exponential factors, they get multiplied, so the arguments just sum, and you get the integral, which is the integral over the union of two spaces, right? So this is this picture of gluing spaces together. And then you have, well, each of these two integrals will have some boundary conditions. So to compute the scalar product, you need to take an integral over boundary conditions. So this is kind of additional slide which explains that this is not arbitrary construction, but it can be really realized in terms of certain theory, Chern-Simons theory, and in fact my specific example that I will study here will be based on this Chern-Simons theory with group SU2, and the boundaries which I'll take will be just simple spherical boundaries, S2. I don't need to know much more about Chern-Simons theory. In fact, I'll never use Chern-Simons anymore. I'll just know that my construction comes from Chern-Simons theory. Okay, so what will be states in my theory now? So as I said, I will only consider now two-dimensional spheres as my boundaries, and my three-dimensional space as space which fills voids between these two-dimensional spheres. So here's some example. I can take a solid sphere. Yep. Here I wrote it for non-abelian theories, so if you just forget this term and the trace, that will be a abelian action. Yes. Right. Yeah, so I will be more interested in non-abelian theories, and in fact, for simplicity, I just focus on group SU2, so that's kind of simplest non-abelian case. It will be SU2 Chern-Simons theory. Okay, so first example of a state in this theory is just what is called a three-ball. So it's a three-dimensional space bounded by a two-sphere. That's one example of a state. I can have two spheres or a three-dimensional space which is bounded by two concentric spheres. So that's another example of a state. But this state is already, so if this simple state is a state in this simple factor, Hilbert space of one sphere, then this example is already a state in the product of two Hilbert spaces. Well, there's further examples. You can have, a three-ball with two cavities. That's an example of a state in products of three elementary Hilbert spaces. Well, if I'm studying SU2 Chern-Simons, level K, then it turns out that if I have just a state, well, if I just consider a two-sphere, it corresponds to a trivial Hilbert space of dimension 1. So this is not a very interesting case. To have a non-trivial case, I need to somehow make topology more complex. One way to consider non-trivial spaces is to consider, for example, torus instead of a sphere. It will have a finite dimensional Hilbert space. And people who know a little bit quantum Hall effect, they know that the fundamental state on a two-sphere is non-degenerate. If you go to a higher genus surfaces, then there'll be degeneracy in ground state of quantum Hall effect. So this is similar, this is a connected story here. If I have a sphere, there's no interesting Hilbert space. So what I can do, maintaining this two-dimensional spherical topology, is to start removing points from the sphere. So this is called introducing punctures, for example. So I'll drill holes in these spheres, and well, holes, they have to be extended in three-dimensional spaces, and which means that there'll be holes connected by one-dimensional lines. And in this example, I probably can hardly see, there's a bigger sphere and there's a smaller sphere inside, and there are two kind of lines. Some lines they connect two spheres, and some lines that start and end on the same sphere. So that's an example of a state in this Hilbert space. So one technical slide. So I will explain how to compute the dimensions. So the story is the following. So well, let's go back to the abelian case. Abelian case of Chern-Simons. This kind of punctures, they correspond to charged particles that you can put on a sphere. So if I put n charged particles on a sphere, then spheres that they live in just this closed spherical space. I mean, there is no infinity in this space. And the electric field lines, they should end somewhere. They cannot go to infinity because there is no infinity. So there is a constraint, a natural constraint for particles, charged particles on the sphere, for this construction to make sense. The sum of the total charge should be 0. Okay, so there cannot be no net charge in a closed space. So here's the same thing, but instead of charge, I'll consider different characteristics. It's a non-abelian theory, so instead of charge, I will consider spin. So if I put n particles with spin 1/2 on a sphere, they have to be in a singlet state. So they have to form a combination that the total spin of this configuration is 0. So this is how we'll construct count the dimension of the Hilbert space. So the dimension will be the number of different possibilities to form a spin singlet state on a sphere. And in particular, my minimal example will be 4 points, 4 punctures on a sphere. So this corresponds to, and I will consider fundamental representation. This is a product of 4 doublets. So how I can form spin 0 combination from 4 spin 1/2 particles? Well, I can compute a tensor product and find that there are only 2 singlet combinations in this case. So the dimension of this Hilbert space is 2. If I have a sphere, if I have 4 punctures, then there will be that this corresponds to a Hilbert space of dimension 2. And how I can draw that? Well, I can draw this by taking these lines and at points and connecting them with lines. There are different possibilities how I can connect 4 lines together. There are 3 possibilities, in fact, if the lines are not oriented. But since the dimension is 2, any 3 choices will be linearly dependent. So I only need 2 combinations, so I will choose these ways of connecting lines, points, and this will be my basis. And this basis is not necessarily orthogonal, so in principle I will need to add this piece here to make state 1 orthogonal to state 0. Well, there is some small comment here. Well, the story is not that simple, so because really, if I'm talking about Chern-Simons theory, then the particles are not characterized by just spin of SU2, but spin of Kac-Moody algebra, representation of Kac-Moody algebra. But I can forget about this story if I keep this parameter k of Chern-Simons very large. This is kind of classical limit of Chern-Simons. And in that case, the story is very similar to just a representation theory of SU2. Okay, so, well, let's now forget about all these technical details. So what I will do from now, I'll draw diagrams, and these diagrams will represent quantum mechanics. And again, I said I have space, Hilbert space of dimension 2, and I will now substitute these diagrams of a sphere, but with simple diagrams where I have collections of points, which I just join in sets. So here is a set of 4 points, and this is one way to connect the points. This is another way, and here is the linear combination, which is supposed to be orthogonal to the first state. So in order to compute the scalar products, in order to compute, for example, this normalization factor, I need to explain you how to really compute scalar products in this model. And as you should already understand from what I told before, if I want to compute a scalar product, this means that I should glue states together along the boundary, so which means I have to connect these sets of points. And clearly, if I just take this state and compute its square, right, its scalar product with itself, you should get a diagram like this. So I need to explain you what this diagram means. It should correspond to some numbers according to an axiom that I mentioned before. So all these scalar products, there are some numbers, and I have to explain to you how to compute these particular diagrams. I mean, in principle, this is known in Chern-Simons theory, but what was noticed by Edward Witten in particular, that Chern-Simons theory, these correlation functions in Chern-Simons theories, they are related to what is called Jones polynomials in mathematics, were discovered separately in topology and statistical physics. So instead of explaining how to do this in Chern-Simons theory, I'll explain you how to compute Jones polynomials. So I have these diagrams here, and the rule is the following. So if I have just a single circle, I will replace this circle by a number. I will call this number D. If I have a kind of a link, so I have any arbitrary diagram of a closed line and a separate circle which is in no way tangled with this link, then I'll just replace the result by the polynomial of the link times the number D. Okay, so I'll just you can already see that in this case the result will be D squared. This is just D, and here D squared again. So it's just using these rules. It's very simple calculation. So you can already check. You can already normalize all the states, compute scalar product, normalization factors, and so on. I mean, there can be also a more complex situation where instead of these simple circles, you can get what is called a knot, right? Knot is a circle which is a diagram which may have some self-intersections, so something like this, right? So how can I compute this case? Well, in this case, I'll have another tool which is useful called skein relation. I'll use that, diagrams. Any crossing is actually a linear combination of two diagrams without a cross. So if I apply this rule to any of the intersections here, I'll have linear combinations of diagrams with coefficients, and each of these diagrams in the end will be just a collection of circles, like in this case. So I can apply rule 1 and rule 2. Well, here there are some coefficients. They are related to the number D as follows, and these parameters can be related to the parameters of the Chern-Simons theory in this way. Okay, so in principle, with these rules, you can already compute all correlation functions in this quantum mechanics. So now I want to come to this main discussion and explain what is entanglement, what are the properties of entanglement from this point of view. And first, let's just think of what means entangled versus non-entangled in this picture. So we said that topological spaces are mapped to some quantum states. And here I have examples of two quantum states. So which one of them is entangled, which one is not? I mean, just by looking to this picture, you already know the answer, right? Clearly, this is non-entangled because it's separable. So here the meaning of separability is the same as in quantum mechanics. So this is entangled because there's a connection between two parties. There's part A, call it Alice, and part B, called Bob. So in this case, there's no correlations between them, here there is a correlation. So just as simple as this. Well, I mean, this is kind of a guess, so how I can confirm this? One way I can compute what is called von Neumann entropy or entanglement entropy. And I'll do this here by computing this entanglement entropy using replica trick. What is replica trick? Well, replica trick, technically you need to compute what is called density matrix, reduced density matrix, and you compute certain power n of this density matrix, you compute trace, then you compute make a analytical continuation of this n to arbitrary values, and then you compute the derivative with respect to n and the limit of n going to 1. So let me explain how this will look in this topological picture. So first I compute the density matrix. So what is density matrix? Well, density matrix is just a square of a state, right? If we have a state, then density matrix is just a matrix which is a square of the state, where one of the state is just taken Hermitian conjugated. So here, what this procedure means, I just take my states and I duplicate them, and just for convenience, I draw one upside down. So this is the density matrix. In principle, I have to normalize it. So I normalize it by dividing these matrices by the trace. How do I compute traces in this case? Well, trace means that I have to connect spaces of similar origin with themselves. So I have to compute sigma A, glue sigma A to sigma A, sigma B to sigma B. This will be the trace. So in first case, the trace will be just a pair of closed spaces. So that should be substituted by numbers. Here is this number, appears as a normalization factor. Well, apart from that, I need to compute what is called reduced density matrix. And reduced density matrix means that I'm only interested in the degrees of freedom in part A and not in B. So I have to trace out, as we say, the part B. So how do I do this? I need to compute this partial trace. Again, tracing means just connecting sigma B with itself. Especially in the second case, how do I do this? So I have this kind of a phone receiver, and two copies of this phone receiver, and part B is this one. So computing a trace means that I should connect, glue together these two pieces. So the reduced density matrix is simply a cylinder. Okay? So this is the result here, reduced density matrix. And here, this donut here is a normalization factor. You can, apparently, if you just compute the trace of that again, that will be a donut. Just glue the beginning and the end of the two cylinders. Okay, so you compute this trace to any power of this density matrix, because it's easy to multiply this density matrices. You just put one matrix on top of each other. So if you just have two cylinders, put one cylinder on top of the other one and glue them, and you get a cylinder again. So nothing changes. So any power of this matrix is again a cylinder. The only thing that changes is the normalization factor. So here's the result for the trace of nth power. It just will be this normalization factor to power 1 minus n. But in the first case, it's actually, the result is much simpler, because anytime you multiply this matrix, you get the same thing. So in the end, the trace of this density matrix to power n is just 1. And when you compute the logarithm, so this is something you need to do. I mean, this derivative here in the limit when n goes to 1 essentially means that you replace the result by the logarithm of the matrix rho in power 1. So in the first case, the logarithm of 1 is just 0. Logarithm of that is, well, this kind of symbolic expression where I didn't tell you exactly what this thing here is. So this donut, it is actually a number. So how do I compute the number? Well, I didn't tell you exactly what is the structure of the states here. That might really have some additional topology inside, like these lines that I drew before, maybe some holes and so on. Well, so it's important that whenever there is an internal structure, it doesn't spoil this property that when I For example, square the cylinder, it produces the same cylinder. And one example of that, I can put just lines in a very simple way, just lines which do not tangle, they do not cross. In this case, by multiplying this cylinder many times, I'll get the same cylinder. So in this case, the answer will be this cylinder is kind of identity operator, and what I'm computing here is a trace of identity operator, which is dimension of the Hilbert space. So in this case, the entanglement entropy is the logarithm of a dimension of the Hilbert space. We call such states maximally entangled. So that's an example of a maximally entangled state with one caveat. So if my original sigma in the state here, if this is just a sphere, simple sphere with no punctures, then the dimension of the space is 1. So the log of 1 is 0. So it's not an interesting example. So I need really introduce punctures and lines to have non-trivial examples of entanglement. So the generalization in this case will be this one. I'll have punctures. These punctures will be connected by lines, and these lines they can also link with each other, entangle. So I can have this kind of complex situation in general. And what we already know that this situation corresponds to a maximally entangled state. You can choose the basis that I showed you before, gluing these basis states here, and you can check that this is exactly 0, 0, 1, 1. So that's an example of a Bell state. It's maximally entangled. So this is clearly a separable state. Again, using the same basis, you can find that this is just a 0, 0 state. This is more complex, so you can also compute this state explicitly. But this is an example for more general entangled state. It will have, counterintuitively, this kind of state will have less entanglement, although it has a lot of topological entanglement. There will be less quantum entanglement because this one is the maximally entangled state. Okay. All right, so now that we understood what entanglement is in this kind of interpretation, we can also ask what are the different kind of entanglements that exist. There is this story in quantum resource theory, in quantum information, that depending on the properties of entanglement of a given state, it can be used for different quantum tasks. So one state is good for one quantum problem, another state is good for another, is a good resource for another quantum problem. So how do I classify here? Well, in principle, there is an infinite number of topologies. So I can draw like an infinite number of complex tangle diagrams. So by itself, this topological classification is not very interesting because it's infinite. And for quantum tasks, you want to have a finite classification, typically. So I need to invent some kind of coarse graining where I reduce this infinite number of topological classes to a finite number of classes. So one way to do this, well, first let me mention the results from quantum information. There is a well-known classification called classification by stochastic local operations and classical communication, SLOC. This classification tells that, well, let's consider two quantum states. If I can transform one into another by some local operator, and this local operator may not necessarily be unitary but has to be invertible, then these states are equivalent from the point of view of this classification. And what it means also, since it's not unitary, in this case that, well, the same two states can be used for the same quantum task, but not necessarily both states will solve the quantum problem with a unit probability. Sometimes for the states you will have a certain probability of success in realization of a quantum task. Oh, here's an example of a local operator on my qubit. So I can braid the points on the surface of a sphere. In this case, it will be a unitary operation. I can also have an example of non-unitary operation. So if I just take this maximally entangled state and bring it to this state, well, there is no local braiding. So I cannot just braid lines in one sphere here to produce the state. So that's an example of, but it's invertible. So it's an example of an invertible but non-unitary operation. Well, you can also have a non-invertible operation. This is clearly a projection. just take a state which is a linear combination and you project it onto just one basis state. Well, as far as slog classification is concerned, so as much as I know about the results, is that if you have a pair of 2 qubits, then there are 2 slog classes. The states can be either separable or entangled. Or if you can generalize the notion of a qubit, so if you take states which take values in larger Hilbert spaces, like m-dimensional, n-dimensional complex Hilbert spaces, then the number of classes will be equal to the dimension of the lowest dimension of the pair. Well, if you have 3 qubits, then there are 4 classes: separable, Bell, and 2 classes of what is called genuine tripartite entanglement. They're called GHZ and W. For qubits, this classification becomes inefficient in the sense you can still classify, but the number of classes becomes infinite. So I would like to build another classification and compare it to this slog classification. So what is the natural classification, at least from my point of view here? Well, we have seen this already. So depending on how we wire the space, how we connect the sides with the lines, we have different kinds of entanglement. In particular, we had this maximal entanglement. So what this diagram corresponds to, so there's like 2 sides here, B and A, again, and there's correlations between them. So these lines that I was drawing always, you can understand them as correlations between parts of the system. So this is the maximally correlated, maximally entangled state. This is minimally correlated. There's no correlations between left and right. So that has to be a separable state, non-correlated state. And there are intermediate cases, right? Some partial correlations between left and right. So the question is, can you really draw this kind of diagrams, and whether this will count all possibilities, for example, from the point of view of the slog classification? And I will skip a couple of slides here. The answer is yes. And indeed, here's the result for, let's say, pair of qubits, pair of qubits, pair of qubits with dimension 4, complex dimension 4. Indeed, this is as I told you before. So in case of qubits, there are two classes. Either they are entangled or they are not entangled. In case of qubits, there are 3 classes. And okay, in the bipartite case, when you have just 2 parties, this classification also in the slog case is quite easy. What it tells you that if you have a density matrix, then it's just the rank of density matrix that determines this this class. And these diagrams, they in some sense, they are diagrams representing these density matrices, and they are showing. So you can basically by drawing this kind of basis that I showed for qubits, you can show that all of these diagrams, they are matrix of certain rank, where the rank decreases from right to left. So here for n equals to 4, this is the maximal rank. This is, well, in this case it will be rank 4, rank 3, rank 2, rank 1 matrix. So just in case of slog, you cannot, you can write down the matrix, you can compute the spectrum, you can do what is called Schmidt decomposition, compute the number of values. But in this case, you have this nice diagrammatic representation, which you do not know how to make in case of matrices. But of course, we like diagrams, and in the end, these diagrams that I'm drawing is also a way of multiplication of matrices. But in this case, it's a very natural way, and in terms of something which is intrinsically there in the topological theory. Well, for general case, it actually doesn't work that nice. So if you go to 3 qubits and you try to, draw the diagrams which represent all kind of correlations between 3 parties, and since it's a qubit, there are 4 points in each party, and these are all diagrams. But then you'll find that actually there is certain relations, linear relations between diagrams. In particular, the first 3 diagrams, the first 4, they are the same thing. They're just representing the totally separable state. And the 2 diagrams here, the next 2 diagrams, they are what is called biseparable. It's a Bell state with an additional qubit. And there's only one diagram for truly tripartite entanglement, while in slot classification there are two classes. There's GHZ and W. So you can compute explicitly the expression in terms of the basis by gluing those basis states that I shown before. And this is the expression for the state. It is indeed a GHZ kind of state. So in this case, there is no W state. So it somehow is not captured by this topological classification. And the reason for that is that this topological representation of quantum mechanics is not full in the sense that it is discrete, right? The number of states is continuous. It's non-countable, while the topologies are countable. So you should understand topological quantum field theory as a representation of quantum mechanics in the sense of, well, you can really construct, well, on one hand, you can construct it as any linear combination with arbitrary coefficients you can always construct. But in terms of, the diagrams, particular diagrams, you do not have enough diagrams to represent all the states, but you can approximate any state with any given accuracy, with initially defined accuracy, because the states that you have, they are dense in the space of all states. So it turns out that W states is apparently follows, well, W is a whole class. There are infinitely many states, but they are not dense. So they measure zero in the space of all quantum states of 3 qubits. And topological classification, well, topological description does not capture this class. So you can approximate them by considering, you can start tangling, braiding the lines here, and you can always approximate W states in this way, but there is no easy, simple diagram for W state. Okay, so now let me just go to more simple discussion. I'll just explain properties of entanglement in terms of these diagrams. So first property of entanglement, one of the basic that we learn is called monogamy. So what is monogamy? Monogamy, well, the simplest version of monogamy tells you if two states, two subsystems of a system are maximally correlated, maximally entangled, well, if one is maximally entangled to the second one, it cannot be entangled to a third one. And this is very easier to understand in terms of this diagram of correlation. So if A and B are maximally entangled, then they used all these lines that they have to connect between themselves. So there's no way A can connect to C because there's no lines left for A to connect to C. So that's an example of monogamy. Well, you can ask, how about this case? In this case, there is some topological entanglement, and well, there will be some entanglement indeed in this case, but you can use those skein relations that I showed before and draw this diagram as a linear combination of a simple diagrams. It will have in particular a term which is like this. There's no correlation between A and C, but there will be also terms where A and C are correlated. Since it's a linear combination, A and B can no longer be maximally entangled. So this is how it works in this case. Well, there's an interesting properties of this particular class of states that are used for classification, that they satisfy the area law. So if you probably heard, and some of you probably heard about this result in ADS-CFT correspondence, that in these gravity models, the entanglement entropy is computed by the area of some minimal surface in a high dimensional space, whatever. The idea is that they show that indeed entanglement entropy is not extensive quantity, it doesn't scale as a volume, but rather as a boundary of some boundary area of the boundary of the system. So here you have a very similar property, and you can also derive this kind of area law, but for this particular classes of states. So in particular, state like this is maximal entanglement. What it means is really this area law is that when you consider this diagram with the maximum number of lines connecting left and right, what this diagram represents are two spheres. So you can have two spheres, one inside of the other, and they are connected by 4 lines. So you have one sphere and another sphere inside of it, and then there are 4 lines that connect the 2 spheres. If you try to cut this diagram in the middle, which means let's insert another sphere in the middle, or it is not necessarily a round sphere, you can deform it, but the minimum number of lines that you'll cut in this way is always 4. You cannot cut the picture into 2 parts without cutting at least 4 lines. Well, this state is different, so you can cut it. There is some section where you can cut it, where you just cut 2 lines. So this property of the area law would tell you that the entanglement entropy will be actually proportional to the minimum number of lines that you can cut by this section here. And it's easy to show using this replica trick, which I explained before. And in the end, there is a connection between the number of lines and entanglement entropy. So if you compute really how the dimension of the Hilbert space depends on the number of lines, and it is given by Catalan numbers. If you take the number of lines to infinity, then there's an approximate formula for this number. Well, it's 4 to the power n divided by some power of n, and the logarithm of this behave asymptotically as 2n log 2. So which means that there's log 2 coefficient, log 2 of entanglement entropy for each line. And well, this is quite natural. So each line is kind of corresponding to a spin 1/2 particle. So there is an entanglement entropy of log 2 for each particle like this. So the conclusion in this case is that you can measure entanglement entropy in terms just by counting lines. And then you can use this property to compute certain inequality for entanglement entropy, very well known inequalities. Well, let's consider first the property called subadditivity. If you have a system which has subsystem A and B, then the entanglement entropy of the union of 2 subsystems is less or equal than the sum of the entanglement entropies of 2 subsystems. And we can derive this using this approach in terms of the states that I described before. So let's draw A and B, and there is a complement of A and B. So if A and B, well, there can be another subsystem here, which not necessarily include the union of A and B. So then there are lines that connect A and B, certain correlation between A and B. There's a correlation between the complement and A and B. Let's call NA the number of lines that emanate from A, and B will be a number of lines that emanate from B. And then there's also a number of lines that connect to the complement, NAB. And LAB will be just a number of lines that connect A and B. So then you can just write a very simple expression here. The sum of the number of lines NA and NB is just the number NAB plus twice the number of lines that go between A and B. Okay, this is like very simple equality, just counting lines you can write them down. And then there's a very simple conclusion you can make that this is apparently greater or equal than NAB bar. Okay? And from what I told you, these numbers, they compute entanglement entropy, so you immediately get this subadditivity property of the entanglement entropy from this calculation. In fact, you can notice that well, this LAB, or twice this number, is the sum of NA plus NB minus NAB bar. And if you interpret this in terms of entanglement entropy, then this quantity is called mutual information. So in this language, mutual information is just exactly the number of lines that connect A and B. Well, actually, I would correct the definition of the mutual information here, because it's actually twice the number of lines. So I think a more natural definition for mutual information would be, well, this quantity divided by 2. So that's the amount of mutual connections between the 2 sides. Well, in the same way, you can also derive strong subadditivity relation. This is another quantity, another inequality that exists for entanglement entropy. It's a very hard one. Here you can also derive it by just easy computation calculation for number of lines. Well, unfortunately, there's not much time left, so I would, well, let me just briefly explain this thing here. So you can use this kind of topological logic to derive new tools for quantum information. And here I want to explain how you can derive a new measure of three-partite entanglement. So the idea is that is this idea that I explained before. So if something is entangled, it must be connected. So if there's no connection, then there is zero entanglement. And if you think of state, the three-partite state as diagram like this, where there's some unknown correlations between A, B, and C, the density matrix will, for subsystem A would be something like this. So you just multiply, you trace, well, you trace out parts B and C. So if B and C are both, these lines are broken, then row A will give zero entanglement entropy. But if, for example, B or C have non-broken lines, then there will be non-trivial entanglement entropy. So if you want to really identify three-partite entanglement, you need to compute more than just rho and A. But if you think of this in topological way, so you just need to build something which will break when either B or C they have lines that are broken. And these are two examples. Just build a ladder which will break when whatever connections, correlations between parties, well, when either of the parties is really disconnected, then the chain is disconnected. And then if you compute the analog of the von Neumann entropy, this result will give you zero if either B or A or C are not entangled. Okay, here I was just checking how this works for in general. I was comparing here this kind of measure that I introduced with another measure which is called rectangle. I will not explain this here because I want to go to this last part, which is quantum algorithms. So let me first explain quantum teleportation in this language. So you might have heard of quantum teleportation already. So the idea is the following. So you have two parties here, Alice and Bob. Alice has some unknown state. She might know, might not, what the state is. And she wants to transfer the state to Bob. So to do this, Bob needs, Bob and Alice, they need to share an entangled pair. So as I explained before, this diagram corresponds to a maximally entangled pair of qubits. So in the most simple way to explain how Alice can transfer the state to Bob is to say, okay, she just needs to connect the lines and then the Bob will get the state in his possession. Well, this is a bit oversimplification. If I just follow, I need to explain some particular steps that needs to be done in this protocol. So here's the original protocol of quantum teleportation. So there is two entangled states that Alice and Bob share, and there is this additional state psi that Alice wants to transfer to Bob. So she needs to apply certain quantum operations here. This is called C0 gates. There's some Adamar gate. She needs to apply measurements. So she needs to measure two qubits that she has and communicate the result to Bob. She has to call Bob and tell, I measure it, spin up here and spin down here. And then Bob, depending on the information he receives from Alice, he can recover the states of Alice by a set of operations here, conditional on the measurement of Alice. So how this can be built using the topological circuits? Again, there is a pair of entangled qubits shared by Alice and Bob. There is a state which is unknown in principle. And so here is the diagram. So what Alice should do, she needs to apply certain gates. And this gate is just braiding of lines. So this is how she, after that she needs to do a measurement. Measurement means that she has to project her qubits on certain bases. And this basis is shown here. And it is convenient here to use not the orthogonal basis, but a more simple basis of states that I was using here, right? So there's just these two kind of vectors. They're not orthogonal, but they are linearly independent. So in this case, if you can try yourself, so what really Alice needs to do. So she will need to measure the qubits, which means that she will, after her measurement, she will replace these caps with one of these four combinations, which means, for example, here she measured that the spin is in the in the orientation up. Here is up, here is down, and down, and it's the same for the second spin. And then, depending on these results, she will have to say what Bobs need to do by phone. She will tell him what to do to recover the original state. Well, if two states are she measured two zeros, she needs to tell Bob do nothing. So Bob will need to apply the cylinder, but the cylinder in this case will be just nothing. Well, if there's 0 in the first case and 1 in the other, then Bob will need to braid two lines of his qubit, and then he will recover. So you can just do it yourself. Just try, for example, a state like this and apply. Well, I will not draw exactly the operation that needs to be done. So there's some line braiding, but in the end, if he applies what Alice tells him, he will recover the same state in the end. So that's the idea. Well, another example is the very actually related protocol, which is called of communication called dense coding. Well, since I don't have much time left, so I will not explain, but this is kind of suggestion. So you can also try to play with this braiding and see that if you follow these instructions, then it will work like this dense coding protocol in quantum information. So, okay, let me just conclude here. So the point of the talk was to show you that topological quantum field theories, they give nice tools that allow to kind of image the quantum states. So you can draw diagrams representing quantum states, and then you can start playing with these diagrams and learn something about how quantum mechanics works. And in particular, I try to explain how some very well notions, phenomena of quantum mechanics are explained in this language, like entanglement, its measures, properties, and how quantum communication works. I didn't explain it very well, but that's the idea. And well, finally, I have to say that there are certain limitations, of course, in this case, exactly because topological theories, they are not provide a one-to-one map between topological spaces and quantum states. So some apparently properties of quantum mechanics are not so simple in this description, like W state that we discussed before. Okay, thank you very much for the attention.
Questions?
Hi. So thank you for this nice talk, Dmitry. Really interesting subject anyway. You mentioned that in order to get the entanglement entropy, you need to draw a line and count the number of lines that cuts this line, right? So I was wondering if how this method connects with the entanglement entropy that you use. Like you have some area law, but you also have some topological terms that is usually denoted by the gamma term. So how this connects with this counting of lines here? Can you say some words?
Right, so you want to ask how this is connected to this topological entanglement entropy.
Which are intrinsic in topological. That term is not related to the area law, right? So I don't know if I missed something, but
no, I think it is a very good question, and I think in fact the answer is that there is a relation, but they probably need to think a little bit how exactly this works, because that's the story. The whole story of topological quantum computation is related. Well, I think in that case, there is part of a story which I didn't tell here. Maybe because I restricted all my consideration to the case of spheres, but if you go to higher dimensional to different topologies, then the story will be a little bit different, and the counting will be a little bit different. So I'll be able to have non-trivial entanglement entropy without any punctures, without any lines. And yeah, I didn't explain this here, so I think this is the right way to explain this, but I need to think a little bit more. I mean, that's a very correct question here. So in some way, it was kind of intentional to restrict to the case of spheres to avoid the discussion of higher genuses and so on.
Thank you. So you showed that it's not possible, like to capture, for example, W states using this representation. So I was wondering, I guess that should be true also for some operations. So you wouldn't be able to represent all operations by using this.
Yes. So this is closely connected. Sorry to interrupt you, but I think this is closely connected to the story of universality of quantum computation. So you have a discrete set of states and discrete set of operators. And you may ask the question, is it enough to solve any quantum problem, right? And then indeed, there's a small difference between topological quantum computation in the usual sense, which assumes certain specific value of the parameter k. And then you can have Fibonacci anyons, Ising anyons, and so on. And Ising anyons, for example, they are not universal. You cannot build universal quantum gates with permutation of Ising anyons and so on. So I'm actually considering kind of analytical continuation in K, so it doesn't have to be integer, but or I say that K is very large, so I should not worry about these things. But in any case, there is the number of topological operations is discrete, so it means that I can only solve any problem at best with a given precision. I cannot get a full solution. But this is very similar to our general situation. We have computers. We cannot write arbitrary number on a computer because we have a discrete number of bits, right? So then anything that we compute is with a certain precision.
I see. Okay, no, that's exactly what I wanted to ask. And I also have another question. So you showed the teleportation protocol, and you showed like the simplified version before without the measurement. So in this case, that part of the top that I guess that could represent some kind of measurement. We know that is not allowed. So is this captured by this formalism? Like, why is that not a possible measurement that you can make?
Well, it is a possible measurement in the sense that I want to measure. So the result of my measurement somehow was projecting on the Bell state. So my question is rather to you: can I do this as a measurement? So usually we understand the measurement is projecting on basis states for each qubit. But in principle, it's just a more complex measurement, right? Let's assume that somehow I managed to do this projection, which I have no idea how to do. But that's why I needed to really go back to what really people define in this quantum in the teleportation protocol. Here, just I have two qubits and I project on basis state. But there's nothing different from just these simple operations. This complex measurement is nothing but this is just an explanation. That's the same thing. What you would really do in your lab. Well, this is my understanding.
The problem is that that kind of measurement is, I mean, I'm not sure what it corresponds to, but for example, I think it would correspond to like a measurement on a normalized maximally entangled state. So it would be an ill-defined measurement, I think. But I was wondering if this is also something that is captured by the formalism.
I think there's no really much difference between what you can do in quantum mechanics and with this formalism. It's just here I'm just saying, well, I'm projecting the result on a very specific state. You would do the same in quantum mechanics, right? But I don't know like, how. I mean, I'm not very familiar with with protocols in general, and what's besides behind is this kind of operations technically. But again, my statement is I'm just trying to reproduce here what is already known in quantum mechanics. My point here is rather that this topological representations can help you to maybe invent something more interesting, which is not so obvious in terms of matrices. But as far as known things are concerned, well, there's some. I think there's some nice representations of all these protocols in terms of just braiding lines, right? But it is no different with ordinary quantum mechanics. Just a subclass of what you would do in quantum mechanics.
Okay, thank you.
Further questions?
Yeah, yes. Well, about a similar topic as the previous question, there are certain states and operators that you cannot capture in this topological description. And from a practical point of view, I guess that may not really be a limitation, because you can, as you said, you can approximate them arbitrarily well. So you can go. But from a more conceptual point of view, it would be interesting to know if the states that are not captured by the topological description can be characterized some way. So that, can you say in advance a state having so-and-so property is captured and a state having this property is not captured? Is there a common characteristic of those?
Yeah, I think I'm kind of having some intuition about how W is different. And maybe this is actually known in quantum information theory. So for me, it appears like W state is more quantum than the GHZ state. So GHZ state is a good notion also in the classical limit. But W state is not captured by this kind of semi-classical states. And well, I would say apparently the same problem should exist in the lab, that if you want to generate certain kind of state, well, you have certain resources available. So depending on your resources, it will be easier or not or hard to construct a specific state. So in this kind of lab that I have here, W state is complex. I mean, you cannot really construct it from what you have, from the simple building blocks. But that's the same problem should exist. I'm not sure how hard in general is to construct W state. Raphael should certainly knows. But maybe it's actually easier. But here, I see. Okay, so here it's kind of different. And in fact, one observation that I didn't make here, but I'm trying to connect this kind of states that I consider that are given these simple diagrams with the story of ADS CFT correspondence, where these simple diagrams, they kind of correspond to classical gravity states. So GHZ would be something that is captured by classical gravity. But if you want to describe W state in terms of gravity, you need to go to quantum gravities. You cannot just deal with classical gravity.
Can I ask another question? This is on a different topic, on something you said at the beginning. One thing we do in quantum mechanics very often is time evolution. And in some parts of quantum computation, we also do time evolution. But you don't have a local Hamiltonian. So how do you time evolution?
So here you have a discrete time evolution. So time evolution is basically you construct your quantum protocol. So it's just in a sense of quantum computer. Yeah. You have some quantum protocol. The protocol is your evolution, is your Hamiltonian.
Okay. Just a discrete number of steps.
Yeah, exactly.
You define the steps.
You may think of maybe continuum limit of that. So you can maybe consider periodic application of certain levels of quantum gates and take a continuous limit, and then you will recover some local Hamiltonian, and that will be your evolution. Or in general, because you have certain arbitrariness of these gates that you can put, that would mean that your Hamiltonian is time dependent. It's not constant, and may be very complex.
Yeah, that makes lots of sense. Thank you.
Further questions?
So thanks for the nice talk. I have two questions. The first one is related to the comment on the anion things you said. So at finite k, we have the usual story of Kitaev's modular tensor categories and all that stuff. And there are some anions which are known to actually do universal quantum computation, even that they have like a discrete structure, like the Fibonacci anions.
Fibonacci,
Yeah, they are universal, right? So can you interpret in some sense what you're doing is like some large k limit of that story, which is not some sense well defined by the modular tensor thing, because it's
Well,
also
Fibonacci anions is just a specific value of k. I
right.
think it's
Right.
well, it's 3 probably. K equals
Three.
yeah, right.
But
So, but I'm taking the limit of large k.
I see.
So this is a classical limit of Chern-Simons theory in some way. Or even I want to really do an analytical continuation and not leave these integer values for k, because then I'm looking at topological theory in more general sense. Because something that I didn't describe here, didn't mention here, is that if you take a finite k, this is related with this Katz-Moody and Vesumino-Witten. If you take finite k, then it means that there will be some additional linear relations between states. And we were discussing right now, the fact that here you have a discrete number of states. But if you take finite integer k, in fact, the number of states will not only be discrete, but even finite. So you have quantum mechanics in terms of a finite number of states and operators.
I see. And
Well, as we know, for certain values of k, you can still do universal quantum computation.
okay, I see. So we are dealing with a semi-classical description of some sorts. And a related question is of the ADS-CFT comment. How can we interpret this as actual ADS-CFT? Because in 4 dimensions, for example, we have a graviton or something, and things are not topological. But can we think these are some sort of semi-classical limited S3 CFT2 dimensions or something?
Yeah, I'll tell you first maybe some heretical thing is that actually any gravity is some kind of topological theory, because Einstein equations, they're variation of the action with respect to the metric. And if you do not have any meta, then variation of the action with respect to the metric is 0 in any theory of gravity, right? But this is exactly the way we determine the T mu nu, the stress energy tensor, right? So in any gravity, stress energy tensor is 0.
Right.
So there's no local Hamiltonian in any theory of gravity. But okay, this is oversimplification. But we know that lower dimensional examples of gravity, like 3-dimensional gravity, 2-dimensional gravity, they are topological theories. So in the first place, of course, I think of connection in terms of these theories.
Okay.
And I don't know how far you can push this analogy.
I see. That's it. Thank you.
Dmitry, so yeah, thanks for the talk. I have a few questions, but I think time is running. So maybe 2 suggestions, like something that if you haven't thought, maybe we should talk about. We should
Yeah,
think
that
about
was.
together.
I have to thank you for the dense calling. So you suggested to look into it, and in fact, it turns out to be like a nice, simple exercise to do.
So I have 2 more. I think they are more complicated this time.
Good. Yeah.
So one is like looking at the states that you have in error correcting codes. So like there you also have like highly entangled states, like and you have a huge theory behind them, and also like things that are connected to condensed matter, like the story codes and this sort of thing. So it might be interesting to see what these are from this topological perspective. So I have no idea how to do that, but might be interesting. And the other thing is that, so you said that you can prove the strong subjectivity very easily, right?
Well, no, I can demonstrate it. To prove it is a different thing. So one problem here is that this is true, and this is the story actually, the same story in ADS-CFT correspondence. Well, they claim they can prove strong subjectivity very easily, and there's no, in general quantum mechanics is not easy. And the trick here is that you actually reduce to a subset of states. You do not consider arbitrary quantum mechanical states. Here too, I mean, I can prove it very easily for these states, which I called connectome, right, which are diagrams with lines without intersection. But if I consider more complex state, then it will be hard to prove. And it means that in gravity, you should also go to quantum level and try to prove the same formula in quantum level. And I'm not sure it is easy.
Okay, so it's like in these.
So it is actually a
SFT,
trick, right? So
no, because
was
like
not
in
clear
quantum
in the
mechanics,
beginning that
proving these
gravity.
information inequalities is very hard. So there are a lot of open problems there. So, I mean.
Yeah, so if I reduce it to a simple class of states, then I can prove it, yes, very easily, but not in general.
Okay, thanks.
And yeah, indeed, I think also looking into error correction codes is like very interesting question. I was trying to approach it from different ways, but I think it is possible indeed.